Pre-calculus students, welcome to today's notes 9.3. We're going to take a look at geometric sequences and series. Now we've already looked at arithmetic. Geometric is when instead of adding or subtracting, we multiply or divide. So here we go. A sequence is geometric if the ratios of the consecutive terms are constant. So you can see the setup here. If you had consecutive terms 1, 2, 3, and so on, the ratio would be constant. So A2 divided by A1 is the same as A3 divided by A2, and so on infinitely. R is your common ratio. Another way to say that is, are you multiplying or perhaps dividing by the same thing each time? So let's take a look at that and see on number 1, 2, 6, 18, 54. I hope all of you see that quickly and say, you know what, Mr. Hale, yes, we are multiplying by 3 each time, so that's most definitely a geometric series. All right, here's our next one, number 2, 1, 2, 6, 24. What I'm looking at is times 2, times 3, times 4. So this one is not constant. Actually, what it is you have a factorial situation going on there. So the next number would be 120, then 720, and so on. Now the last one, number 3, again, this is geometric. This time our R value is what we're multiplying by. Some of you may look at this and say, well, we're dividing by 2, which would be correct, but let's change it to multiplication and make it an R value of 1/2. All right, so we're going to start with a little formula here. To find the nth term of a geometric sequence, you can see that a sub n would equal a sub 1 times r to the n minus 1 power. I want to give you an alternate version of this formula that we'll use from time to time. We won't use it immediately, but we will pretty soon. And instead of using a sub 1, I'm going to call it a sub m. So that way we don't always actually have to know the first term. You can use any term. So as long as you know 2 of them, you can use this formula. So a sub n equals a sub m times r to the n minus m is a more general formula than the one you see up here. So it might come in handy, sometimes avoids the middleman where you don't have to go back and start by finding the first term. Okay, so on number 1 though, we've got the first term is 3. We know the ratio is 2. Our instructions just say to find the first 5 terms. I'll tell you what I'm going to do. I'm not going to worry about writing a formula here when all I have to do is say, well, I know the first term is 3, and I know each step of the way I'm multiplying by 2, so that is done. All right, let's take a look at number 5 here. This time we know the third term is 27, and the ratio is 1/3. So I'm going to treat this one a little differently. I'm going to say, okay, I know the third term is 27. I'm multiplying by 1/3 on each step, so my next number would be 9, the number after that would be 3, so this is the third, this is the fourth, this is the fifth. Now you might just look at this sequence kind of going backwards and say, I kind of get the idea here, we're multiplying by 3 if you go the other way. So this second term would be 81, and the first term would be 243. On to the next slide, number 6, find the 15th term of the geometric sequence with the first term is 16. I'm going to go ahead and write that down. A sub 1 is 16. And the constant ratio of 1.27. And again, we're trying to find a sub 15. So what I need to do on this one is I'm going to actually set up the formula, the nth term formula. So I'm going to say a sub n is equal to a sub 1 times the r value 1.27 to the n minus 1 power. Now from here, all I really need to do is just plug in what I know, which is I know that a sub n, instead of a sub n, I'm looking for a sub 15. So let's do 16 times 1.27 to the 15 minus 1 power. And at this point, I'm pulling out the trusty calculator, and I'm getting a value of 454.33. That is rounded, but it works. Okay, let's take a look at the next one. The fourth term this time is 125, and the 10th is 125/64. Now this is the first time we've run into giving 2 terms, neither of them being the first, so it requires just a little bit more thinking. And if you look back one slide, the alternate version of that formula is really going to come in to play on this particular problem. So what I'm going to do is use the 2 terms we know. So I know a sub 4 is 125, and I know a sub 10 is 125/64. And I'm going to plug these two numbers into that formula. I'm going to use the larger one, a sub 10. And I say larger, I mean the number that's further in the sequence. In this case, it's obviously not a larger number, is equal to 125 times, now this is what I'm looking for, is that common ratio. I don't know the common ratio, but I do know that 125 is the fourth term and 125/64 is the 10th term. So I would take this to the 10 minus 4 power. And then we would be able to go ahead and say, all right, so that's r to the 6th. I'm going to divide both sides by 125 as well, doing a couple things at once here. And then r to the 6th is 1/64. By the way, if you wanted to solve this algebraically, take both sides to the 1/6 power. That gets rid of your exponent. Remember that whole thing there? So the 1/6, and what you get is r is equal to a nice lovely 1/2. So here we go. We've got a sub n, I'm going to do the nth term formula here, is equal to, oh wait a minute, we don't know the first term, do we? Well, so I'm going to adjust that. I could go and find the first term, but I'm actually not going to. I'm going to go ahead and just use the one I know, or one of the two that I know. I'll go with the 125/64 because I know we all love fractions. And actually, let me do this. Instead of writing a sub n, we're looking for the 14th term. Let's just go find the 14th term. So this is to the 14 minus, well, 125/64 was the 10th term, so 14 minus 10. I know I'm throwing a lot at you, but you can do this, I promise. So here we go. 1/2 to the 4th power would be 1/16. 16 times 64 is 1024. So we have a value of 125 over 1024. That's the 14th term. Up next, we're going to take a look at a couple of sum formulas. We're going to start with finite geometric sequences. Finite, of course, means it has an end, and we're gonna use the formula that you see here. And I know there's a lot going on, but basically, it's saying the sum of the n terms for the summation of I equals 1 to n of a sub 1 times r to some power I minus 1 is equal to. And so what you need is you need the first term, you need to know the r value, and you need to know the number of terms. That's really all that we have going on. So we're going to use that formula right there. Need to do a little calculator work with this one, but it's really not too bad. So let's walk through number 9 together. We need to find a sub 1, our first term. Well, this starts at k equals 1, so we would have 1 minus 1. That's 1.3 to the 0, which is just 1. So a sub 1 is equal to 5. We also need to know our r value. It's 1.3. And we need to know the n value is the only other variable, which would be 12. That's just the number of terms in this particular sequence. We're ready to write our sum now. So the sum of the first 12 numbers here is equal to a sub 1, which is 5, times 1 minus our r value, which is 1.3, to the n power, divided by 1 minus 1.3. I know this looks a little ugly, but you can punch that thing into your calculator. It doesn't mind ugly numbers. Be careful with the order of operations. You guys with TI-84s might want to consider hitting alpha F1. Might be a good friend to you on this particular problem. And I've got the sum of those 12 numbers being about 371.63. All right, let's look at number 10. I'm going to actually let you guys do this one on your own, but first I want to show you an alternate way you could write this. Some of you may not like the fact that this starts with n equal to 0. If you'd like to, you could rewrite this summation notation, increase that by 1 and that by 1. So this is the same as 1 to 10, but then we have to make just a little adjustment because we'd end up moving a step ahead. So instead of saying negative 5/4 to the n, we got to start where this exponent is 0. So we're going to go n minus 1. So those two forms are identical. They're just different ways of writing it. So pause the video, work through this one on your own, and then compare your answer to mine. You can see my work now on number 10. It's kind of interesting that we end up with a negative total here, but it actually makes sense because with this particular sequence, the numbers are getting larger and it alternates signs. And since the 10th term would in fact be a negative number, it goes plus, minus, etc. This is a negative, so the sum would be negative. If you went to 11, this would be a positive number. It'll just go back and forth. And remember, this is a sum that we're talking about here, not actually the 10th term. That would be a different calculation to find the 10th term. Okay, now we're going to do something that may seem a little bit strange. We're going to find the sum of an infinite, and yeah, you can do this, geometric series. Now we can only do it in one scenario. We can find the sum of an infinite geometric sequence, or series, I should say, if the r value is less than 1. And by r value, perhaps saying the absolute value of r is being less than 1. Because what happens is this, as n approaches infinity, if r is small, we're talking about a number like 1/2, 1/3, 1/17, etc. And you increase the power, this r to the n value becomes smaller and smaller and smaller till it would hit 0 at infinity. So really what you have is a much simpler formula, which is a sub 1 times 1 over 1 minus r. Now, why is it that if the r value is greater than 1, the series has no sum? Why don't you write down an idea there and then share it with your neighbor when you get to class next time. So let's take a look then at number 11. We'll do this one together. Find the sum of the geometric series. Again, when you look at this formula, really what I need to know is I need to know a sub 1, which in this case would be 3 times 0.75 to the first. 3 times 0.75 is 2.25. We also need to know the r value, which is 0.75. Notice on this particular formula, that is all we need. There is no n value that we need to concern ourselves with because, in fact, the n value would be infinite. So here we go. The sum for this particular series would be a sub 1. So 2.25 times 1 over 1 minus 0.75. Let's try that again, 0.75. And we can simplify that. This is really just 4 right here. So this is 4 times 2.25, which is exactly 9. All right, why don't you guys pause the video, do number 12 on your own. All right, welcome back. You can see my work on 12. Probably the key to this one is to realize that the k value starts at 0. So 3/4 to the 0 is 1 times -3 gives you your a sub 1 value. You can see the rest of the work right there. All right, on to the last slide. Find the rational number representation. Now what we're going to do here, for instance, number 13, we're going to consider 0.47 repeating to be a pattern that looks like this. 0.47 plus 0.0047 plus 0.000047, and so on. Okay, so it's a repeating sequence, and really you could call it a series since it's infinite. And so let's think about what we know. Well, we know a sub 1 is 0.47. That's the first term in the series. And we know the r value each time we're multiplying by 1/100th. So here we go. We're going to go ahead and find the infinite sum is how we'll treat this. So the sum is equal to a sub 1, which is 0.47. If you prefer, you could write it as 47/100ths. I'll go ahead and do that this time. Times 1 over 1 minus 1/100th. And we can do some simplification there. And you get 47/99. So 47/99 is exactly the same as 0.47 repeating. All right, the last one, number 14. We're going to treat it very similar to what we did on 13. I'm going to help you get it set up. So instead of just starting out with this, I have to think of it this way. I have to think I have a 0.5, but then my sequence begins 0.021 plus 0.00021 plus, and that would continue. So pause the video, try to do number 14 with that information on your, and I basically considered the sequence of the repeating 21s separately from the 0.5. you can see the work over here where I found that this pattern is 21 990ths, and then I just simply did 1/2 plus 21 90ths, and it gave me the value of 96 1/65.